Welcome to this lecture series in real analysis. In this lecture, we will discuss the Heine-Borel theorem or the Heine-Borel theorem, I don't know the pronunciation, which is the most important theorem in real analysis. And primarily what we need to know is the notion of an open set. So fix a subset U of R, we say that it is open if either it is empty or if it is non-empty, then for each point x in it, there should exist some epsilon, positive epsilon, such that this open interval, whose endpoints are x minus epsilon and x plus epsilon, is contained in U. So for every point x in U, there should be some room around it, which is also contained in U. So that is the definition of an open set. We discussed this at length previously. And with that, let us proceed. Here are some problems for practice. And now let us get started. So we will define what is called a cover. Fix a subset A of R, a collection script C or fancy C. This is read as script C. I will read it as fancy C also. So let fancy C be a collection of subsets of A. Sorry, subsets of R, I mean. Collection of subsets of R. And we say that this is a cover of A if the union of all the things in fancy C contains A. So in notation, it just reads A contained in the union of all the things in fancy C. In other words, every element of A is in some element of fancy C. So the terminology is well chosen. If you visualize A as some subset of the reals, covering is just literally covering. It is overshadowing everything that is there in A. So a collection of subsets of R is called a cover of A if everything in A is in some element of the collection. Okay, let's maybe see an example. So this is a very, very simple example. Let A be equal to R. Maybe I'll change the color. So we are taking the entire set of real numbers, and then if you define this as the collection of all the open intervals of length 2 with the left endpoint varying over the integers. So in pictures, what is this script C? This is the set of real numbers. This is 0, 1. So I'm marking all the integers. ... So the elements of script C are this open interval, that open interval, that open interval, and so on. And clearly you can see from the picture that fancy C covers the entire set of real numbers because the union of all of these things is the entire set of real numbers. Okay, on the other hand, if we had defined C as this thing, then this is not a cover of the set of real numbers because no integer lies in the union of all the elements in fancy C. So very, very simple example. Okay. Now we can define what is an open cover. So fix a cover of something. So this will be a cover of a subset A of R. We say that C is an open cover of A if each element of fancy C is an open set. Very simple definition. So an open cover is just a cover where we have an extra constraint that every element of the cover must be an open set. Okay, so this is an example of an open cover of the set of reals. You can easily construct examples which are not open. You can just put closed intervals here and that would still be a cover, but it wouldn't be an open cover. All right, and now we can define one more notion before we can prove the Heine-Borel state and prove the Heine-Borel theorem. So what is that definition? It is the definition of it is the notion of a subcover. So fix a cover of some subset of reals, then a subset D of C. So what are we doing? We had a collection of subsets of R. We are considering a subset of it, meaning we are throwing away some of the things here and retaining some of them. So a subset D of C, or you can also call it a subcollection, if you will. So a subset D of C is called a subcover of A if it is also a cover of A. A very, very simple definition. Basically, a cover may have too many things, too many unnecessary things. A subcover gets rid of some of them. So here, I don't know if I will be able to construct a subcover. Let me see. Yeah, I mean, no, I don't think you can. So this might not have a subcover, but you can easily construct examples. For instance, you can artificially add things to it, and then this would be a subcover of anything that you subcover of any artificially added one. So this definition is fairly simple. I don't think one needs any examples to to understand it. Before I proceed and state the Heine-Borel theorem, let me just make a very simple remark that if C is a cover of A and B is a subset of A, then C is also cover of B, clearly. And so that's it. So if something covers A, then it also covers every subset of A. Very, very simple fact. All right. So here is the theorem. You fix two real numbers, A and B, where A is less than equal to B. Then every open cover of this closed interval admits a finite subcover. What does that mean? If you have an open cover, let's say C of this guy, there will be a finite subset of it, which will also cover this. So that's all that this is saying. This pink thing is only saying that every open cover of it has a finite subset, which is also an open cover of it. So closed intervals have this interesting property. This property is not there with open intervals. Maybe I will not forget to give an example. But anyway, as of now, let's just try to prove this. And if I don't forget, I will give an example where open intervals may have an open cover which do not admit any finite subcover. Okay. So let's prove this. And the proof technique is quite interesting. This is the proof is not very hard to follow, but the technique is quite interesting. It is basically a form of mathematical induction, or the well-ordering principle, if you like. So let's fix an open cover of the closed interval. And we want to show that there is a finite subset of C which covers the closed interval. All right, so we will make a very simple reformulation of the problem. We will define a set S as those elements in the closed interval such that this sub-closed interval, by that I mean this smaller closed interval, can be covered by finitely many elements of fancy C. All right. So this is the set of those points in the closed interval a comma b, those x's such that this much can be covered by finitely many elements in fancy C. And the theorem only asks us to prove that B is an S. That's exactly what the theorem is stating. So we want to show that B is an S. This is our goal. All right. So first note that S is non-empty. S is non-empty because A is an S. Now, why is A in S? Let me not write anything. Let me just explain. We have this closed interval a comma b. Saying that A is in S is same as saying that this closed interval is covered by finitely many elements of C, which is to say that the singleton is covered by finitely many elements of C, because this closed interval is precisely the singleton. And saying the singleton is covered by finitely many elements of C just says that there are finitely many elements of C whose union, if we take, A will be in that union. But we know that this closed interval is covered by fancy C, and therefore every element of this closed interval is there in some element of fancy C. In particular, A is also there in some element of fancy C, and therefore the singleton is covered by finitely many elements of fancy C, namely just one element of fancy C. So this is clear. S is non-empty, and clearly S is bounded. S is bounded simply because it is a subset of a bounded set. So a non-empty bounded set always has a least upper bound. So let maybe this deserves its own color. Let me choose a notation before we proceed. So what is a good notation? Let's say S is in supremum of. S is the supremum of S. Yeah, an okay notation. All right. So what we need to do, or what we want to do, is that this S is actually equal to, I mean, this is a little bit weaker than our goal, but at the very least we want to show that this is equal to B, right? Anyway, we will get there. So this is our supremum. All right. First, we will show the following. So we claim that S has something strictly greater than A. So we claim that there exists X in S such that X is greater than A. We notice that A is clearly in S, but we want to show first that there is something strictly greater than A also in S. So in this closed interval, there is some point here, something greater than A, such that this entire closed interval is contained in finitely many elements of, or the union of finitely many elements of fancy C. Okay, again, this is also very simple. So to do this, let me maybe try to give a full argument for this. So why is that? Let U be in fancy C be such that A is in U, because A has to lie in some element of fancy C. So let's say that the name of such a thing is U. But U is an open set because fancy C was an open cover. U is an open set, so there is some epsilon greater than 0 such that this interval is contained in, this open interval is contained in U. And let me kind of trim this out. We just need this much to be contained there. So the previous one was a little bit stronger of a statement, but we are just happy with this much. In fact, let me further terminate this. Further trim this out. Let me just say epsilon by 2, or maybe I'll do it in the next line. This implies that A plus epsilon by 2 closed interval, this is contained in U, right? So Pictorially, what are we saying? We have this closed interval a comma b. U is some open set which contains a. And since it is an open set, there will be some room around a which is contained in U. Now the room goes both ways, but we have in this line we have only talked about one direction of it. So to do this diagram more justice, this is A, that is B, and let's say this much is U, some open set which looks like an open interval in my drawing, but it doesn't have to be. So that is U, and there is some semi-open interval contained in U. In fact, there is an open interval around A that is contained in U, but we are content with the semi-open interval. And this is A plus epsilon. But this also means that if we just look at this point, A plus epsilon by 2, this closed interval, which is A comma A plus epsilon by 2, is contained in U. So in particular, if you look at this number, A plus epsilon by 2, this is an element of S. Why? Because this closed interval is contained in finitely many elements of C, or in the union of finitely many elements of C, because it is contained in just one element of C. So that's it. So this proves that actually there exists something in S which is strictly greater than A. This is a very simple claim. Okay. And now our next claim is, we claim that our supremum that we defined, so we claim that S is also in capital S. S was defined as the supremum of S, but we claim that it is actually lying in S. Okay, so why is this? Suppose not. We will go by contradiction. All right. Now, since S is here, why is S here? S is little s is the supremum of capital S, but capital S is a subset of A comma B, this closed interval. So that implies that supremum of S will also be in this closed set. So just note that S is in this closed interval. Since that is the case, there is some element of fancy C which contains S. Some element of fancy C, let's call it U prime, such that little s is in U prime. Okay? Diagrammatically, so something like that. And now let delta, since U prime is an open set, let delta be such that this is contained in U prime. So since U prime is an open set, there is some room around S that is contained in U prime. Okay. And this is the final observation. Note that some point of this interval must be in S. Right? Because if that were not the case, if no point here were in S, then every element of S would be smaller than S minus delta. And therefore the supremum of S would be strictly smaller than S. So the reason why this is true is because the supremum of S is little s. S cannot have anything greater than little s, that is true, but if we further assume that it doesn't have anything from this interval, then the supremum of S cannot exceed S minus delta, but that is a contradiction to the choice of little s, to the symbol little s. So some point of this interval must be there in capital S, and what that means is that there is some there is some point in that interval. So let's call that point, maybe let's call that x0. So x0 is a point in this interval, which is there in capital S, which means what? Which means that this closed interval is covered by finitely many elements of C. So this closed interval, this much, is covered by finitely many elements of C. Let's say those things are C1 up to Ck. So the union of this contains this interval. But to this just append U prime. These are also finitely elements of fancy C, and they cover more than that. They cover, in fact, the entire thing, this entire closed interval A to S. But that would mean that S is in capital S, right? So you can fill the details. I have said it in words and pictures. So this actually proves our claim. Okay, so this has been justified now. So this is in capital S. And now finally we can show that S is equal to B by the same kind of reasoning. So finally we claim S is equal to B. And the reason is the same. If S is strictly smaller than B, as shown in this picture, then again you find a U prime which is containing little s. U prime lies in fancy C. And since we have already shown that little s lies in capital S, this interval is covered by finitely many elements of C. And what that means now is that whatever those finitely many elements are, let's call them again C1 up to Ck, you append U prime to it, you get another finite subset of C, fancy C, which covers more than the previous one. It covers this bigger closed interval, and that means this point, the point here, lies in capital S, but this point is greater than little s, and hence the supremum of capital S exceeds little s. So that's the reason, and let me maybe write down the details. I mean, it's the same thing I'm going to write down, what I've just said. So we have A comma B, let's say, suppose that then S is strictly smaller than B, and here we can mark it out, S, and let U be in fancy C such that S lies in U. Also, since by the previous claim little s is in capital S, this is covered by finitely many elements of fancy C. So say, let me write U1. So these finitely many elements be such that this entire thing is contained in this union, but that implies that, so before I continue, this is fine. Again, here we will choose a delta. So let delta greater than 0 be such that this thing is contained in U. Because U is an open set, you can find such a delta. So we have that, and now since little s is in capital S, this is covered by finitely many elements of C, and therefore we get U1 up to UK. I've written C1 up to CK here, but I meant to write U1 up to UK. U1 up to UK, the union of them contains the closed interval A comma S. But then this thing, A comma S plus delta by 2, this is contained in this union. So what happened? This much is already contained here, and this interval S, so this interval S minus delta comma S plus delta, this is contained in little u, this is contained in capital U, and therefore in particular the closed interval S comma S plus delta by 2 is contained in capital U. So if we just add that part to this closed interval, meaning all we are doing is we have this closed interval union this closed interval. Let me write that again. This closed interval union this closed interval. This is contained in this union that. U1 union dot 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 UK, that takes care of this part, and union U, that takes care of this part. So this thing is contained there. But what is this thing? This thing is just that. But that implies that S plus delta by 2 is in capital S, which contradicts the fact that little s is the supremum of capital S. Little s was the supremum of capital S, and this conclusion contradicts that. So that's it. This proves our claim that S is equal to B, and therefore B lies in S. We already showed that S lies in S, but since S is equal to B, B lies in S, and that was our goal. B lies in S. So that proves the Heine-Borel theorem. It is a good idea to wait here, as long as you're not comfortable with this proof. It is a good idea to stay on it. It's a simple proof, but maybe this idea of this particular way of proving it is somewhat new. So with that, I want to end this. As usual, like, comment, share, subscribe, and I will see you next time.